Good evening, ma'am.
Good evening, sir. Yes, sir, you are audible.
Okay, ma'am. Thank you so much.
Sir, you can start, sir.
Okay, ma'am. Good evening, students. In this class, we are going to discuss the solutions for the numerical problems for which you took a test last weekend. Okay, so I gave you a question paper consisting of 15 multiple choice questions last week, and we are going to discuss the solutions for some of the numerical problems. Okay, so first of all, we are going to discuss the solution for question number 3. I will be showing you the question now. Okay. So first of all, I would like to show you the question. Okay. Are you able to see my screen, students?
Yes, sir.
Yeah, thank you. So the first question I think I have already discussed during the class last week itself. The third question we are going to discuss now. The third or maybe the fourth question. Okay. The fourth question we shall discuss now. Two metal spheres, one of radius r and the other of radius 2r, respectively have the same surface charge density. Okay. So let me repeat that again. Two metal spheres, one of radius r and the other of radius 2r, respectively have the same surface charge density sigma. They are brought in contact and separated. What will be the new surface charge densities on them? For that, you are having 4 options, out of which you have to choose the correct option. Okay. So two metal spheres, they have the same surface charge density but different radii. They are brought in contact and then separated. So we have to find out the new surface charge densities on them. Okay. So before we are going to discuss the solution for this problem, we need to understand the question. So when you bring the two metal spheres in contact with each other, okay, charge distribution happens between the two spheres until the potential on both the spheres become equal. Okay. So whenever you bring the two charged bodies in contact with each other, the charge redistribution happens between the two charged bodies until the potential on both the bodies become the same. Okay. So here also you are actually bringing in contact two metal spheres. Both are having some charges. So when you bring these spheres in contact, the potentials on both the spheres will become equal. Okay. So using this hint, we are going to proceed with the solution for this problem. Okay. So for that, first of all, I am going to open the whiteboard and share the whiteboard with you. So now I have opened the whiteboard. Okay. We are going to discuss the solution now. We have two spheres. So let us consider the first sphere here. And the second sphere I am going to denote by a different color now. Okay. So in the problem, what they have given is the radii of the two spheres are capital R and 2R. Okay. So this one let me consider as capital R, and this one I am considering as 2R. Okay. So here I am considering this one as sphere A, and the radius of this sphere I am considering as R. and this thing I am considering as sphere B, and the radius is 2r. Okay. Now what they have given is the surface charge densities on both the spheres are equal initially. So the surface charge density, let me consider the symbol sigma A equal to sigma B. That means surface charge density on sphere A is equal to sphere B. Okay. So what is the equation for the surface charge density? So actually, the equation for surface charge density is charge per unit area. So this is sigma A. So initially the charge on sphere A, let me consider as QA. So divided by 4 pi into capital R square. Okay. And sigma B, let me consider that we are having a charge QB on it initially. So QB divided by 4 pi into 2r the whole square. Charge per unit area means the surface area. So I am actually using this equation. So from this equation, okay, from this equation we can find out the QA and QB. Okay, so QA is actually equal to sigma A into 4 pi into r square, and QB equal to sigma B into 4 pi into 2r the whole square. Okay, so this implies QA equal to sigma into 4 pi r square. That means 4 pi sigma r square, and the QB. So this implies QB equal to 16. Okay, this 2 square is taken as 16. So this will be 16 pi sigma r square. So what is the total charge initially? Okay, total charge Q equal to QA plus QB. This is the initial charge. Okay, Q equal to QA plus QB. So that will be 4 pi sigma r square plus 16 pi sigma r square. So this will be 20 pi sigma r square. So this is the total charge initially. So the QA and the QB, the total charge. Okay, that is 20 pi sigma capital R square. After bringing these two spheres in contact with each other, now what will happen? There will be redistribution of charges, and due to that, now after bringing the spheres in contact, okay, after bringing the spheres in contact, you are having QA prime as the charge on sphere A and the QB. Okay, why it is changing? Because the charges will be redistributed until the potentials on both spheres become equal. Okay, so after redistribution, the charge on sphere A is QA prime, and on sphere B it is QB prime. Now I have told you that the charge redistribution occurs until the potentials on both the spheres become same. Okay, so what is the potential? So potential on VA should be equal to VB. Okay, so the formula for potential is QA prime divided by 4 pi into r square. That will be equal to QB prime equal to 4 pi into radius square. So that is 2r the whole square. Okay. Sorry, that's not r square. That is r. Here also it is. And we need epsilon naught also. So epsilon naught. So here it will be epsilon naught into capital R. And here it will be epsilon naught into 2r. Okay. So from this you can find out the ratio of QA prime and QB prime. QA prime by QB prime equal to what you will get, you will be getting 1 by 2, because you can take this 4 pi epsilon naught r on the other side and this QB prime to the left hand side denominator. So when you take this to the numerator here, 4 pi epsilon naught r divided by 4 pi epsilon naught into 2r. So that will be 1 by 2. Okay. So this equation will become 1 by 2. So QA prime by QB prime is equal to 1 by 2. So what is the meaning of that? Here, according to the conservation of charges, this total charge 20 pi sigma r squared can't be created or destroyed. Okay, the total charge before bringing the two spheres in contact should also be equal to the total charge even after the spheres are separated. So this total charge Q equal to 20 pi sigma r squared cannot be destroyed or created. So after bringing these two spheres in contact, the new charges will be distributed like this in this ratio 1 by 2. Okay, 1 by 2. So using this ratio, we are going to find out the charge on sphere A after bringing them into contact. That is QA prime and QB prime. We are going to find out. So for that, I am opening a new page. So QA prime is to QB prime is 2. So this is 1:2. Okay, 1:2. So according to the concept of ratio, so now this QA prime will be equal to, we have this 1 here. Adding these two numbers, it will be 3. 1 plus 2, it will be 3. So what will be the charge on QA prime according to the concept of ratios? That is 1 by 3 into total charge Q. Similarly, QB prime equal to 2 by 3 into total charge capital Q. So this is equal to 1 by 3 into 20 pi sigma r square. Okay. So sigma r square. So what is sigma? The surface charge density initially. Okay, the surface charge density initially on both the spheres, that I consider as sigma. So this is 1 by 3 into 20 pi sigma r square, and this QB prime will be 2 by 3 equal to 2 by 3 into 20 pi sigma r square. So now we have to find out the new surface charge density on both these spheres. Okay, the new surface charge density on both these spheres we need to find out. That will be taken as sigma 1 and sigma 2. Okay, so for finding sigma 1, you have to consider QA prime divided by 4 pi into r square, and sigma 2 it will be QB prime divided by 4 pi into 2r. The radius won't change, into 2r the whole square. So this will be QA prime is nothing but 1 by 3 into 20 pi sigma r square whole divided by 4 pi r square. So this sigma 2 it will be 2 by 3 into 25 sigma r squared whole divided by 4 pi into r squared. Into 2, 4 actually, because you have a 2r the whole squared, so 2r whole squared means that will be 4, okay. So 4 pi r squared into 4. This is how you need to take 4 pi r squared into 4 into 4, right? So here you can cancel out some quantities. Here the pi r squared will be cancelled, okay. So this pi r squared and this pi r squared will get cancelled, and this 4, this 20 can get cancelled. So you will be getting pi by 3 sigma, okay. So after cancelling out these terms, this pi r squared and pi r squared, and this 4 and 20, that is pi by 3 sigma. So sigma 1 will be pi by 3 of sigma. Sigma 1 equal to pi by 3 of sigma. And the sigma 2 will be equal to, here also you can cancel out some terms, that is this pi r squared and pi r squared, this 4 and this 5, okay. So that will be 5 by 6, okay. That will be 5 by 6. So this pi r squared, this pi r squared, and this 4 and this 20 will be 5, and this 2 and this 2, okay. So 5 by this 3 will be taken to the denominator, 5 by 6 sigma. So it will be 5 by 6 sigma, okay. So sigma 1 equal to 5 by 3 sigma, and sigma 2 equal to 5 by 6 sigma. So this is given in option D, and option D is the right answer. Do you all understand the solution for this problem, students? Anyone have any difficulty in understanding this? You can tell me. Students, do you all understand the solution for this problem?
Yes, sir.
Yeah, anyone have any doubt? Anyone have any doubt on this particular problem? You can unmute yourself and you can talk. Is it clear, students? Is it clear to all of you? Okay. I think it is clear to all of you. So I am proceeding with the next thing. Okay. The third question now I will be discussing with you a little bit. Question number 3. So question number 3, here you see the variation of electrostatic potential with radial distance r from the center of a positively charged metallic thin shell of radius r is given by the graph. The variation of electrostatic potential with radial distance r from the center of a positively charged metallic thin shell of radius r. They are asking us to find out the option which shows the correct variation of the electrostatic potential with radial distance r from the center of a positively charged metallic thin shell. So that is nothing but a sphere. Okay. So here the radial distance r has been given in the x-axis, and the electrostatic potential has been given in the y-axis. Okay. We need to find out the correct graph which shows the variation of electric potential with radial distance r. And you need to understand one thing, that as far as a sphere is concerned, okay, the electrostatic potential is same from the interior of the sphere to the surface of the sphere. Okay, that means the electric potential is constant from the interior of the sphere up to the surface of the sphere. So the electric potential remains constant from the interior to the surface. That means it is a equipotential surface from the interior to the surface. So up to the point where you have the radius of the sphere, the electric potential is constant. So in option B you have this. So in option B you can understand this, I think. So here the electrostatic potential is constant from the core or the interior to the surface of the sphere. Okay, surface of the sphere means you have the radius of the sphere as capital R. Up to this point, the electrostatic potential remains constant. Okay. After that, the electrostatic potential decreases with an increase in the radial distance r. And why it is so? Because you have this relation V equal to Q divided by 4 pi epsilon 0 into R. Okay. So this relation, according to this relation, the electrostatic potential is inversely proportional to the radial distance r, and this relation holds in this region. Okay, only in this region, because from the interior to the surface, okay, from the interior to the surface, you have the electrostatic potential as constant. This region, okay, for this region, the electrostatic potential is constant. So you have a straight line. So from capital R, there is a decrease in potential. That means when you move away from the surface of the sphere, you are having a decrease in potential. According to this relation, so you have like this. So the correct option for this question is option B. Do you all understand this, students?
Yes.
Yeah, anyone having any doubt on this? Have you all understood, students? Is it clear?
Yes, sir.
Yes, thank you so much for your response. And we shall move on to our next problem. Okay. And do you want to specify any one problem in that question paper for which you need to discuss the solution? Do you want me to discuss any specific problem?
Sir,
Yes, tell me. Yeah, tell me, student.
sir,
Tell me.
sir, can you do problem number 7, sir?
Problem number 7, right?
Yes, sir.
Okay, we shall do. So first of all, we shall see the question now. Here you have identical charges minus q are placed at each corners of a cube of side. Okay, identical charges you have, and the identical charges minus q are placed at the each corners of a cube of side B. Then the electrostatic potential energy of a charge plus q placed at the center of the cube will be. You have 4 options, and we need to select the correct option. So you need to understand the question first. Identical charges minus q are placed at each corners of a cube of side B. Okay. So each corner of a cube. So before that, let me ask you a question. How many corners does a cube have? Totally, how many corners are there in a cube?
Sir, 8.
Eight
Absolutely right. Absolutely right. So totally, you have 8 corners. Okay, 8 corners in a cube. Okay. So from that, what we can understand that is you will be having totally 8 potential energies here. Okay, 8 pairs, that is minus q and this plus q, minus q and this plus q, like that you will be having totally 8 pairs. Okay, and all the 8 pairs potential energy will be summed up and it will give you the total potential energy. Okay, so let us consider that now. So let me open the whiteboard. Let me see if there is a cube here, okay, in this shape. There is no cube, we have to draw it manually. So this is a cube. And you have a charge plus q at the center, okay. So that's what has been given in the question. You have a charge plus q at the center of the cube. So let me consider that here. So here you will be having plus q. And you are having charges minus q at each of the corners. You have charges minus q. Here one minus q and here you are having another minus q. So here you are having here one minus q. And at this corner you are having one minus q. At this corner one minus q. This corner one minus q, and this corner one minus q. So totally there are 8 corners in the cube, and you have identical charges, that is minus q at each of the corners. Totally there are 8 corners and 8 minus q charges are there. So before proceeding further, let me ask you a question. If there are 2 charges, okay, if there are 2 charges q1 and q2 separated by a distance small r, then can you tell me what is the equation for finding out the potential energy, electrostatic potential energy of these charges? Can anyone tell me the charges q1 and the q2 you have, and if they are separated by distance r, what is the equation for finding out the electrostatic potential energy?
Sir,
Yes, tell me.
1 over 4 pi epsilon naught q by r.
Actually, that is the formula for finding out the potential you are telling. I'm asking about the potential energy for this assembly of 2 charges. You have 2 charges here, q1 and q2. The potential energy, okay, there is a difference between electrostatic potential and electrostatic potential energy. So now I am asking you, what is the equation for finding out the potential energy for an assembly of 2 charges here, separated by distance r? Anyone can answer, no issues. Even if it is wrong, then that's also not a problem. You can unmute yourself and you can talk. The side of the cube here is B, okay, as it has been given in the question. This is B, okay. Now, if you have assembly of 2 point charges separated by a distance r, then the electrostatic potential energy is given by U equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R. Okay, this is the equation for potential energy in general. Okay, if you have 2 charges separated by some distance r, then if you want to find out the potential energy for these 2 charges, you have to use this equation U equal to 1 by 4 pi epsilon 0 Q1 Q2 by R. So in the present case, okay, in the present problem, you have a positive charge plus Q at the center of the cube, and you have charges at the corners. So the total potential energy is given by 8 pairs. Okay, 8 pairs means this plus Q and so this plus Q and this minus Q is 1 pair. Okay, like this. Okay, here you have Q1 Q2 by R now. So you have 8 pairs. This plus Q and this minus Q. So this plus Q and this minus Q. This plus Q and this minus Q, and this plus Q and this minus Q, like that. Okay. So like that, you will be having totally 8 pairs. So since you are having 8 pairs, the total potential energy, okay, the total potential energy for our case is 8 into, so here you have 8 pairs, so minus Q into plus Q, okay, divided by 4 pi into epsilon 0 into R. R is the distance between plus Q and minus Q, okay. So since this plus Q is located at the center of the cube, you will be having a body diagonal, okay, you will be having the body diagonal. So from this point to this point, you are having the body diagonal distance root 3b, okay. B means the side of this cube. So the body diagonal distance is given by body diagonal distance in a cube is given by root of 3 into side of the cube, okay, side of the cube. So body diagonal distance is root 3 into side of the cube. Here you have side of the cube is actually root 3b, but the charge is located at the center. So the distance between this plus q and this minus q will be half of the body diagonal distance. So here you need to substitute instead of this r is the distance between the 2 charges. Here this plus q is located at the center. That means half of the body diagonal distance is there between 1 plus q and 1 minus q. So the half of the body diagonal distance is 1 by 2 into root 3 into side of the cube here is b. Okay. So after this, what you have to do? Okay, you have to simplify this expression now. So this 2 can be taken to the numerator. Since it is already in denominator, it can be taken to the numerator, or what you can do is you can simplify this 4 and this 2. Okay, this 4 and this 2 you can simplify. It will be 2 pi epsilon naught. Then this 2 and this 8 can be cancelled out. It will be giving you 4. Okay, so this 2 is in denominator. So what you can do is you can simply cancel out this 2 and this 4, and you will be getting 2 here. Okay. So after that, you will be cancelling this 2 and this 8, and you will be getting 4. Okay. So after simplifying this, your final answer will be minus 4 q square divided by root 3 into pi into epsilon naught into b. Okay. I think this is option B for you. Okay, this is option B. Or option C, okay, minus 4q squared by root 3 pi epsilon naught into b. Okay, so minus 4q squared by root 3 pi into epsilon naught into b. This is option C for you. This is how you need to proceed with the solution for this problem. Okay. So after this, do you have any doubts in any specific problem?
So question 12. Sir.
Question number 12. Okay. So question number 12. Are you able to see the PDF file now, students? The question paper which I am sharing with you now.
No, sir.
You are not able to see that. Okay.
Yes, sir. Now, yes, sir.
Now it is okay, right? Okay. So you can see this question now, question number 12. Okay. Question number 12. Two identical capacitors C1 and C2 of equal capacitance are connected as shown in the circuit. Terminals A and B of the key are connected to charge capacitor C1 using battery of EMF V volt. Now disconnecting A and B, the terminals B and C are connected. Due to this, what will be the percentage loss of energy? Okay. So here you see in the question they have mentioned that you have two identical capacitors C1 and C2 of equal capacitance. They are connected as shown in the circuit. Initially the terminals A and B of the key are connected. Okay. To charge capacitor C1. Okay. To charge capacitor C1. So here you see so in this diagram what they are telling is you have two capacitors C1 and C2 but their capacitance values are same. Okay. So so this C1 you have the capacitance value, let us consider it as C. Okay. This C2 also an identical capacitor, so the capacitance value is C. Okay. So initially you have the key in this position. Okay. So AB position, that means initially using the battery of EMF V volt, this capacitor C1 is charged. Okay, this capacitor C1 is charged. So what is the stored potential energy right now? Okay, so let me solve that question here itself. Okay, so key position AB initially. Okay, for key position AB, the capacitor C1 is charged. Okay, so what will be the energy now? The potential energy stored in this capacitor. The potential energy stored in capacitor C1. capacitor C1. So what is the equation for this now? Do you remember the equation for finding the potential energy stored in capacitor? When you have C and V, okay, when you have the capacitance value and the potential difference value, what is the equation for finding the potential energy? Can anyone tell me? The potential energy, the equation for finding the potential energy stored in a capacitor when you have the capacitance value C and potential difference V.
So 1 by 2 CV square.
Yes, you are right. So it is half into CV square. Okay. So here it is half into C1 V square, but in the problem itself they have mentioned that both the capacitance are identical. Okay? Both the capacitances are identical. So let me consider this as C and this also as C. So the potential energy stored in the capacitor C1 is half CV square. Okay. So now what they are doing is they are not actually switching off this source. Okay, they are not actually switching off this source. Instead, what they are doing is they are actually changing the key position to here. Okay, key position to here. So this is what it has been mentioned here. Disconnecting A and B, the terminals B and C are connected. So here you can see. So the points B and C are connected like this. Okay. Let me use a different color so that you can understand. So here point B and C are connected. Okay. They are not actually switching off this source. They are actually changing the key position to this point. So now what happens? Okay, you need to understand it carefully because here the capacitor C1 is charged initially, and when you include this key position to this point, okay, the charges already stored in this capacitance C1 is now redistributed among C1 and C2. Okay, it is now redistributed because you already have charges stored on this capacitor. Now, when you switch the key position to here, you are actually including both C2 and C1 in the circuit. Okay, and now what happens is both C1 and C2 are in series actually. Okay, are in series. Okay, are in series. So the C1 and C2 are actually included here in series. So now the charges stored in capacitor C1 will be redistributed among C1 and C2. Okay. So now we have to find out the energy. Okay, we need to find out the energy loss actually. Okay, what is the energy loss now? Energy loss is actually given by delta U, okay, equal to half. Now you have both the capacitors included in series here. Okay, so both the capacitors included in series due to the key position like this. So it will be half into C1 C2 by C1 plus C2. Okay, because capacitors in series, when you want to find out the total capacitance, 1 by C equal to 1 by C1 plus 1 by C2. And this 1 by C will be equal to C1 plus C2 divided by C1 C2. And when you need the capacitance, total capacitance, it will be the reciprocal of this thing. So C1 C2 by C1 plus C2. This is the total capacitance. Here also, when you switch the key position to this point, you will be having the capacitances C1 and C2 in series. So half C1 C2 by C1 plus C2 into V squared. V here is the difference in potential. Okay, Difference in potential, initially the potential is 0, now the potential is V. So that will be difference in potential is V squared only, okay. So it is V square. So now what is the loss in potential energy? Half into C1 C2 by C1 plus C2. So this delta U is actually equal to half into C1 and C2 are equal and it is considered as C. So C squared by 2C into V squared. Okay. So this delta U is actually second. So this delta U is now is equal to 1 by 4. Okay. So I am carrying out from here. So half into CV squared by 4. 1 by 4 into CV squared actually. 1 by 4 into CV squared is the loss in energy. Okay. This is the loss in energy. In the question, they have asked you to find out the percentage. Okay. The percentage loss. Okay. The percentage loss in energy. So the percentage loss you can find out by equal to delta U divided by original energy into 100%. So original energy is half CV squared and it has been reduced further. So half 1 by 4 CV squared by half CV squared into 100%. So this will be 50%. Okay. This will be 50%. It is option C. And when you do like this, actually instead of switching off the source, okay, instead of switching off the battery, when you just change the key position, the charges initially stored in capacitance C1 is redistributed to C2. Okay. So due to that, you are having some loss in energy, and that loss in energy is actually 50% in this scenario. Okay, 50% in this scenario. Okay. Do you all understand this, students? Do you all understand this?
Yes, sir.
Yes, I think it is clear for you. Okay.
Yes, sir.
Okay. So next question. Which question you are having doubt actually? Any other question for which you need me to discuss the solution? Any other question, students? So let me discuss question number 13. Okay, 13 now. Before that, let me clear all these drawings so that it won't be confusing to you. Question number 13 is a similar question actually, but you have a minute difference here. So here you have a capacitor is charged by a battery. After this, the battery is now removed and another identical uncharged capacitor is connected in parallel. Okay. The total electrostatic energy of resulting system. So here there's a minute difference between the question which we have discussed previously. There they have given you the circuit. Okay. So in that circuit, so without removing the source, actually they change the position of the key. But here they actually remove the battery and they connect another identical uncharged capacitor in parallel. Now their question is, what will happen to the total electrostatic energy of the resulting system? Okay, the total electrostatic energy of the resulting system they are asking. Okay, so initially, so before that, let me open the whiteboard. And let me move on to the next page. Initially, they have a capacitor and they are actually charging this. So the initial energy U1 is actually half into CV square. Okay. Then they actually disconnect the battery. Okay, disconnect the battery and another identical uncharged capacitor is connected in parallel. Now, what is the total energy of the resulting system? It is, since you have connected two capacitors in parallel, the energies are actually added up. Okay, so half CV square plus half CV square. Okay, because these capacitors are connected in parallel. So when the capacitors are connected in parallel, what you have to do, you have to simply go for addition of both the capacitances, Cp equal to C1 plus C2. Here both the capacitance values are same, C1 plus C2. In parallel combination, the potential difference remains the same. Okay, so half CV square plus half CV square. It will be 2 into half CV square. You can write it this way. That means 2 times the initial potential energy. That means the potential energy of this system now increases, okay, by a factor of 2. As you can see here, since the battery is not connected, so the potential energy increases by a factor of 2. In the previous problem, actually the battery is not disconnected, only the key position is changed, and also the capacitors were connected in series in that scenario. But here the capacitors are connected in parallel, so the total potential energy or electrostatic potential energy increases by a factor of 2. Okay, so this is option D. So this is how you need to solve this problem. Okay, and we have only 2 more minutes to end the session. If you have anything to ask, you can ask me now. If you have any doubts on the concepts which we have discussed today, you can tell me now. Do you have doubts in any other problem in the test which I have given you last week? Do you have doubts in any other problem, students? Okay. In case if you don't have any doubts in any of the problems in the test which I have given you last week, then we shall keep it this much for this session. Okay. And we shall continue with the concepts of current electricity in our next session. Okay. So thank you so much for joining the session, students.
Thank you, sir.
Yeah, thank you so much.
Thank you, sir.
Thank you, ma'am. Thank you.